Now let's look at what happens for the rounding on the near path. So if you go into the resources section, again you'll have the two files there, so you'll have the Logisim file and also the Excel spreadsheet, so you can go ahead and open those up. So if you open up the Logisim circuit and head up to top level, and then we're going to talk our way through the left hand side here. Now the left hand side here is the near side, and it's a bit simpler whenever it comes to the rounding. Now we know that the near side only will accept exponent differences of 0 or 1, and the right hand side will accept the exponent differences that are going to be 2 or greater. So if we were to look at the spreadsheet, what would be happening in the left hand side, we would have an exponent difference of only 0 or 1. So if it was an exponent difference of 0, it means that this row 8 here, which is the y value, it will not be shifted out because there is a 0 exponent difference. So if there's a 0 exponent difference, it means that there's nothing getting shifted into these lower 24 bits. So it means that the operation that we're performing is exact, so that is we don't have any rounding associated with it. Now the other option is that the exponent difference is a value of 1. So if the exponent difference is a value of 1, again it means that we're going to shift the y bit over by a value of 1, but shifting it by a value of 1 will only enter one value in here, and that will be the guard bit. We won't have any information for the rounding bits. Now it's not that the rounding bits are all zeros or they're all ones or something in between, we just don't have any information, they don't exist. So therefore we don't need to progress with the rounding on the near path. But we seen that the rounding did occur in the far path, because the far path has got an exponent difference of 2 or greater. So if it's an exponent difference of 2 or greater, it means that we're going to have at least the guard bit here and the first part of a round bit will we will actually have that information, so we will be able to go ahead and perform the rounding on it. So it means that things are a bit easier for us on this side because we just don't need to bother about the rounding. So nothing in this side here is actually changed from the previous video. Now, one thing to note here is that I've actually simplified this a little bit from the previous video. I did actually, in the previous video, we had a guard bit for this far side and a round bit for the far side. And I actually at that time I had a guard bit here and a round bit for the this side as well, but we've taken that out because we don't need it. So finally the guard and the round bit here are going to come down into the final section, which is the rounding. So let's go ahead and we'll talk about this rounding section now. So we've already seen this truth table before, and it's the truth table for the nearest even rounding. Now there's no harm in talking our way through it again just to ensure that you're okay with it. If the guard bit here is a 0, so that's 1, 2, 3, 4 options here, then it doesn't matter what happens with the round bit. The value is always less than the halfway point, so we aren't going to have to add any values on in order to round. So the output here is 0, 0 and 0, 0 in those 4 cases. Now the other 4 cases are whenever the guard bit is a value of 1. So that's these 2 here and these 2 here. Now if it's a value of 1 and the round bit is a value of 1, then it means that we're more than halfway. So if we're more than halfway, so that's in this case here and also in the bottom case. Now if we're more than halfway, then we need to add 1 in order to round up. Now the other 2 options are that the guard bit is a 1 and the round bit is a 0. So that means that we're exactly halfway. So if we're exactly halfway, then the nearest even rounding tells us that we have to go to the least significant bit. If the least significant bit is even, that is it's a 0, then we just leave it as a 0, so the output is a 0. Now the last option here is if the guard bit is a 1 and the round bit is a 0, so we're halfway, and then we have to look at the least significant bit. If the least significant bit is an odd number, that is, it ends in 1, we have to ensure it becomes even. So we ensure it becomes even by adding a value of 1 to it. So we add a value at 1 at this point here. So that's the simple truth table that we're going to use for the nearest even rounding. Now what we want to do is we want to just build that truth table up. And we can do that actually using the tool. And I'll show you how to do that just in a second. But the final circuit is this little circuit here. So this circuit here is just a logical implementation of this truth table. So we've got the round bit and the guard bits coming in, and we've got to get the least significant bit. So the least significant bit is simply the last bit here of our 32-bit output. So that's going to be the least significant bit of our mantissa. So we just take that bit out here, and that's me taking it out, and that's it going in here. So this will tell us whether we have to inject a rounding bit or not according to this truth table. And we would inject the rounding bit here at the very beginning. So what we're going to do is we're going to have a rounding bit, this is this bit here, and it's going to be an addition on to whatever we have here. So we're just adding 1 onto this number here. So the 1 will come in here and it will ripple all the way through. So it doesn't actually ripple all the way through because we don't want it to ripple through to the very top one, because the very top one here is our sign bit. So we set this up so that it will ripple through for up to the first 31 bits, and we take the 32nd bit here, which is the sign bit, and we just bring it back out and we put it back in here. So that means that the round bit only ripples up through the first 31 bits, and that will give us the final output here. So let's go in and we'll see how to build this little thing, little bit of circuitry within Logisim. So I've taken a copy of this truth table. Now what you can do is you can get into main and you can go to project, analyze circuit, and this allows us to put the inputs and outputs in. So from the truth table that we had, which is over here, we can just put these values in for a least significant bit M, guard and round, and also the output. So the first input, we'll call it LSBM, and then we'll call it G for guard, and then there's one R for round, and then the output here, we'll just call it O for out, and we can go to the table, and you can see it's created this little truth table. So now all I need to do is put the values in that we've got for our truth table. So I'll put those in here. So we're going to have 0, 0, 0, and then there's a 1, and a 0, 0, and then a 1, 1. And you can put in build circuit. And you'll see it's just built that circuit for us. So we can just copy this. Control C, and then you can just go into the round here and you could just paste it, and that's what I've done. So that's quite a handy little tool that we can use in order to generate the correct rounding logic. So that covers everything that we need to know about the rounding. Now what we want to do is go in and put some values in and just check it out and see how it compares to the spreadsheet. So thank you for listening. I'll get you on the next video. Goodbye.